Our next two speakers are both from the Yasuda lab. The first one is Amy. I love to say she's tiny but mighty. From, from the day I interview her, she's very soft-spoken, but she's tough. And that's why I knew that she could do great in the light microscopy core. She told me she loves math, she loves physics, she's not scared by big formulas, like I am, truth to be told. And so I knew she was going to be the right fit for the core. And one thing that I still remember of your interview was super sweet. At the end, I always ask to the people I interview if they have any question for me. And usually they ask like when I am going to know about if I get accepted or not, or like how is the day today in the lab. And she asked me, can I do an audition to play at Science Meet Music? And I thought it was so sweet because she's from Dreyfoos High School. She plays the viola, correct? And so I think we can audition with Sean maybe. We have viola, we have Daria with the piano. So hopefully we can have you back for that too.
Hello, my name is Amy Lazarte. I'm from Dreyfoos High School of the Arts, and for the last 6 weeks, I've been working in the light microscopy core on a project from the Yasuda lab, which studies neuronal signal transduction. My part of the project is about correcting image distortions to improve understanding of social memory formation. So if you think back to the first time that you met your best friend or a coworker, you may remember introducing yourself and exchanging names and phone numbers. But then the next time that you saw this person, you probably got straight into a conversation and skipped that formal introduction. This is an example of social memory, and we use social memory to evaluate what behaviors are appropriate in social situations. The Yasuda lab is looking into social memory by conducting several experiments with mice that are free to act in a simulated social environment. In these experiments, mice are introduced to familiar and novel mice, and scientists can view the interactions between these mice. If we can see which neurons light up as a mouse performs a specific behavior, such as meeting another mouse for the first time, then we can connect that behavior to those neurons. However, we still need a way to visualize these neurons lighting up, and we couldn't do this before with a conventional lens because the conventional lens only lets us see the peripheral region of the brain. This is where the GRIN lens comes into play. The GRIN lens is a thin, tiny, cylindrical lens that can be implanted into the brain of a mouse through a minor surgery so that we can see the genetically encoded calcium indicator labeled cells. It's attached to this one photon microscope that the mouse wears like a tiny hat while running around and meeting all its other mice friends. With this lens, we can see deep into the brain in regions where social memories are actively encoded. What's special about this lens is that it continuously bends light throughout its optical path, and it varies the index of refraction within itself. This makes it optimal for surgical implantation into the brain, but just like any lens, it has a certain degree of aberration or distortion. And the manufacturers of this lens predicted that this aberration is called a barrel and pincushion aberration, which is an aberration in which the distortion increases in intensity exponentially as it gets further away from the center. To the eye, this looks like the edges are caved in the barrel distortion or stretched out in the pincushion distortion. The goal of my project was to find a way to correct these distortions so that we can see more cells and use less mice to optimize each experiment and gain real, accurate representations of the neuronal activity going on in the brain. But as of right now, this aberration is just a theory, and we need to verify it experimentally to make sure that we really are looking at the barrel and pincushion aberration. So I mentioned how these distortions primarily affect the outer edges of the field of view, but while I was imaging, I noticed that these distortions also change in intensity along the Z-plane and along multiple color channels. So I used a laser scanning microscope to image this matrix of rings here provided by the Argolite company, And I use this because it's a grid of dots that's very uniform and we know exactly what it looks like, so we'll be able to tell easily if there's any distortion occurring on it. Here on the right is an image of that matrix of rings with the GRIN lens using the 488 nanometer laser, and you can see that the distortion intensity is changing as it's moving along these different depths of the Z-plane. You can also see that these colors aren't aligning perfectly, which proves to us that different colors have different levels of distortion. And so now that we understand our aberrations or distortions, we need to find an approach to correct them, and this was the one that I took. First, I imaged this matrix of rings in multiple colors using the GRIN lens and using an imaging without the GRIN lens. And then I ran these images through the Daybook software, which gave me the measurements of exactly how distorted each region of the field of view was. Finally, I tried to correct these distortions by plugging in my measurements from Daybook into TransformJ. And TransformJ is this plugin into the image processing software ImageJ. So this is the first step of my approach, where I took those raw images of the matrix of rings without the GRIN lens and with two different sizes of GRIN lenses using the 514 nanometer laser. Here, without the GRIN lens, you can see that the grid of dots is very uniform and there appears to be no type of distortion occurring. With the large and short GRIN lens, the center looks okay, but the dots on the outer edges look more like lines or curves rather than actual dots. Then here, with the small and long GRIN lens, the distortion is so intense that a majority of our field of view is actually clouded here, and we can only really discern the dots in the center of the field of view. This proves to us not only that there's a distortion induced by the GRIN lens, but also that this distortion varies between different sizes and shapes of GRIN lenses. This is the second step, where I processed those images through the Daybook software, and I got these heat maps with their own individualized color bar, where the green represents the lowest level of distortion and the red represents the highest level of distortion. So here, without the GRIN lens, you can see that there's a lot of green, while here with both GRIN lenses there's a lot of red and orange. And you may think that these color schemes between these two GRIN lenses look the same, but actually the red on the small and long GRIN lens correlates to about 47 micrometers of distortion, while the red on the large and short GRIN lens correlates to about 27 micrometers of distortion. So this proves that our small and long GRIN lens still has more distortion, and that's consistent with our previous observations of those raw images from the previous slide. So now that we have the measurements we need, we just need to find the right plugin to use these measurements to correct our distortions. Here on the left is that image you saw previously, taken with a large GRIN lens with the 514 nanometer laser. And you can notice these distortions occurring along the outer edges of the field of view. When I put the transformation parameters into TransformJ, if it really is the barrel and pincushion aberration, then I should be able to see here on the right an image that looks like the image taken without the GRIN lens, where all the dots are very bright and uniform. And so these were my results when I put in those parameters. And as you can see, these images look exactly the same, so this proves that the distortion predicted by the manufacturers is actually inaccurate. Even though we weren't able to correct our distortions, we can still learn a lot from this process and the images we took and the measurements that we got from them. So first, we know that this distortion is not the barrel and pincushion aberration, and so this helps out future scientists because they don't have to research into this aberration and go through the process of testing it out. And instead, they can look into new types of distortions, and we will need to find new softwares that recognize these new types of distortions so that we can match the correct software to the correct distortion and correct our images. If we can do this, hopefully we can use the GRIN lens as a tool to see deeper into the brain, to study more about social memory, not just in mice, but in humans too in the future. Thank you to Dr. Ilaria Drago for supporting me throughout this internship, and to my mentors, Dr. Nikolai Urban, Dr. Mary Phillips, and Katie Shirley, for teaching me so much just in 6 weeks. and teaching me all about the microscopes and having confidence in me and guiding me every step along the way. Thank you for all the MPFI supporters with their generous donations and who this internship wouldn't be possible without. Thank you to my fellow interns for making this internship so much more fun, and everybody else at MPFI who make this community so bright and amazing.
Great presentation, Amy. Thank you. Questions?
Have you shared this information with the manufacturer?
Actually, yeah, we're contacting them right now, and so we're seeing if they might know future steps and other aberrations to look into.
It's a great question, and this shows that these interns are doing real experiments, so sometimes you find things that you didn't expect, right?
Yeah.
Any other question for Amy?
Hey, Amy. You mentioned that in your presentation that we're not just looking at the distortions of one color, but you said that the different colors seem to behave differently. Were you able to get any of your results to help with the different color distortions?
Could you rephrase that?
Okay. You said that you noticed when you imaged the field of rings that the different colors looked differently. Is there a way to use the data that you got to fix or overlap the different colors in the different color channels?
So is there a way to overlap the different color channels and to correct those distortions among the different colors? Well, we're kind of looking into it right now by trying to graph the light intensities and see what variance between the intensity of the light is between those different colors.
Yeah, very good. Oh, and just wanted to say, I have actually been talking to several people who have possible solutions for the distortions that you found out, and I have some very exciting things that we could possibly try out in the future. So, because you found out what they are, I knew the right people to contact, and they have some good ideas.
Great job, Amy.